Hi Clinton, I'm Thiru. It's currently 1:55 a.m. right now. Way too tired to talk, but hey, it's for my grade. So we got Kepler-11, and this presentation is about the analysis that we did on the exoplanet graph that you gave us. So let's dive in. And obviously, I'm just gonna brief about Kepler-11. Kepler-11 is basically a system that has a star similar to the Sun, and it's about 2100 light years away from the Earth in the constellation Cygnus, and it has a bunch of planets that orbit its star really closely compared to the Earth, and it's best known for that. So you gave us a flux graph to analyze, and so this flux graph basically plots like the brightness of the star over time. And of course, this graph is from Kepler-11, and they use Kepler Space Telescope, I believe that's what it's called, to monitor the light from the different stars, the light that the different stars produce, right? And the periodic dips that are presented in the flux graph is caused by planets passing in front of it, and it's just called a transit. So I analyzed the dips to collect more data. So I identified the different dips on the flux graph, and each transit is basically like a small drop in the star's brightness. And like the dips are, as I said, were caused by a different planet or maybe the same planet blocking the star's light as it moves across. And or actually I could phrase it betterly, or I could phrase it in a better way. So the dips are basically caused by a planet blocking a star's light when it's orbiting the star, if it makes sense. So I could put it like that, and that's called the transit. So I measured the depth of each dip because the depth of each dip tells us how much starlight is being blocked, which like relates to the size of the planet, because a deeper dip means it's a larger planet and a shallow dip is basically a smaller planet. For example, I found like Kepler-11b is like a really small planet, or like a small planet, due to it having like a relatively shallow dip compared to like Kepler-11g. So we can figure all of that out. And I measured the time between like the consecutive dips of each planet, and this kind of gave me the orbital period, which is key. And this also like helped me figure out how long it takes for a planet to complete one full orbit around the star. And for Kepler-11b, the dips occurred at roughly like 10 to 11 days, and Kepler-11g weirdly is not within the range of 10 to 47 or 10 to 50 days. It takes a whopping like 118 days, which is really weird compared to the different to the other planets. And yeah, so the math. So we were given a table or an Excel with different pieces missing, and so basically we had to figure out the orbital period, which was sometimes provided, the semi-major, the masses. I think we had to figure out both the Earth masses and Jupiter masses for some of them. And I had to figure out the radii, transit data, volume, and then density. So what's presented here is basically a form of Kepler's third law, and this equation is basically like used to identify the semi-major axis of A3, which is basically the planet that you're trying to identify, or it could be either way. And P3 and P1 are like the orbital periods of planets 3 and 1, and then A3 and A1 are the semi-major axes of planets 3 and 1, and I think Kepler's third law says that the square of the orbital period of a planet is proportional to the cube of a semi-major axis of its orbit. So that's what is provided like at the bottom, which is P cubed, and then this weird symbol I forgot the name of that Clinton said in class like once, and then A cubed. And this formula basically helps us figure out the semi-major as we rearrange the equation to find the unknown value, right? And I'll go to the next slide because I forgot to put it in the same slide. So you can basically rearrange this to have A3 cubed, which is basically what you're trying to isolate to get the semi-major, right? And then you take the cube root on both sides, solve for A3, and then you would get your semi-major. So for example, if you had like, I don't know, like 2 days, for example, for the orbital period, and then like 1.5 AU for the semi-major, and 4 days for the orbital period for planet 3, I would plug in 1.52 times like 4 squared divided by 2 squared, and I would just cube root that, or like 1 over power to the power of 1/3, and that would give me the semi-major for like planet 3, and that's basically how you use this formula to find the semi-major, and that's the formula that we used, or I used, to figure out the semi-major for the ones that were missing semi-majors, so it's pretty cool. And then that is the conversion of 1 AU, because when you're solving it this way, it gives you the AU and not in meters. So 1 AU is 1.496 times 10 to the power of 11 meters. And you basically multiply the number of AU that you get through this equation after you solve this equation, and then that would directly give you the semi-major axis in meters. So this is an example that I did for planet G, and as you can see, a squared is 0.910, which is the known variable in this scenario, because you usually use a semi-major of a known to find the unknown, right? So that's a known, and then I just plugged in all the other data, and I got 0.463 AU, right? And I multiplied it by 1.496 times 10 to the power 11, and then I got 6.93 times 10 to the power 10 meters, and that would be my semi-major in meters. So to find the mass of a planet, you have Kepler's gravitation law. So wait, I think I'm tripping. Oh. So for this one, this is the gravitational force equation, I'm pretty sure, and then you have to rewrite it to find M1, which is the mass of your planet. And then Fg is the gravitational force between the exoplanet and the star. M1 is the mass of the exoplanet that we're solving for. M2 is basically the mass of the star, and then you can just swap M1 and M2, it doesn't really matter. And then D is the distance between the exoplanet and the star. So we basically rearrange the equation to solve for the exoplanet's mass, which is M1, right? So we basically rewrite it to get M1 equals Fg times D squared, and then divided by Gm, M to the power 2, or M2. And you basically plug in the values for Fg, D, G, which is the gravitational constant, and then M2 to get your M1, right? So, for example, if I had if I had like 1.1 times 10 to the power of 22 newtons for the gravitational force for Fg, I would plug it into the equation, and then if I had like 1m for like the star's mass or like something like that, I would plug it in, and then there's an implementation that I put like right there they can use, and the distance d is just most likely the orbital radius, the semi-major axis of the exoplanet. And you can also use a known for this one, or you have to figure out the semi-major before you do this. So it's kind of tricky to do it the other way, but most commonly you just solve for the semi-major first, and then you do this to find the mass of the planet. And then the next thing is the radius of the planet. So, oh wait, I forgot. So, also, you gave us, you wanted us to get Jupiter masses. So once you get the mass of the planet, you literally just divide it by the mass of Jupiter to get the Jupiter mass, and which is just really simple, and vice versa. If you get the Jupiter mass, and then you can just multiply it by your mass to get thermal mass. So you can do it that way. So to find the radius of the planet, you have to find the dips. So as I was talking, basically like little dips right there that happens in the graph, and then based on those dips, you find the number of the dip, you plug it in into the square root, and then r squared is basically just I think that's the star's radius squared. So you have to find the star's stellar radius, which is provided in the Excel sheet. So I put like a example right there that I did for G. So basically you find where the star radius or the stellar radius is given to you, but Clinton, you gave it to us in sun radius, so we had to convert it back into a normal one in meters. So you do that, and then you plug it in, right? And then the dip is pretty easy because you already found it, and then you multiply the whole thing, and then you would get the radius of the planet in meters. And if you want it in Earth radius, you just divide it by the Earth radius to get the radius of the planet and Earth radii, and that's really simple. Volume and density, it's pretty simple. You just take the radius of the planet, plug it into the volume equation, and you just put it in decimals and you get the number. It's really simple. And then for density, you just get the mass divided by the volume, and that's it. And this is our completed table. Yay. And then we compared our completed table to actual scientist data that I found online, and some of our radius data were off by like 0.2 or 0.6, because I think I saw Kepler-11 d had radius of like 3.71, but then it was actually 3.18. So I think it was just some kind of computational error on our side. And then most of our semi-major Jupiter masses, Earth masses, and like other data were actually close to the actual data calculated by the scientist. I was actually surprised because it was kind of weird for us to go from like a really easy kind of graph to like a weird graph like this one, but we somehow pulled through and we did really well. So it was pretty good. And some factors that could affect a planet's orbit is obviously the gravitational force. Second, the distance from the distance of the planet from the star, because the star literally determines the amount of gravity that the planet receives, and that kind of messes up the orbit based on how close or farther away the planet is. And the orbital eccentricity is also a thing, because the shape of the orbit affects how far the planet is away from the star, and that also changes the orbit. So, yep. And I don't. So for how habitable Kepler-11 is, I think it's not that habitable because like Kepler-11 has all 6 planets orbiting close by each other, and I couldn't really figure out a equation or some kind of formula that I could plug in our data into, or like external data into, kind of figure out the surface temperature or anything. So I really can't figure out the Goldilocks zone or something like that. And like the provided data, we can't really determine if it's habitable enough for us. So I would assume it's not habitable enough because all the planets orbit really close to the star. And that's it. And then I have citations. And I used a bunch of like articles on it, and then I think the very first one is the research that I used for like identifying the different dips because the picture there was just way clearer. And then the second citation was the one that had the different the table with the different like data from the scientists, like the Jupiter mass and all that, the actual data. And then the other ones were just used as reference. Yippee! Please give me a 4, Clinton, please.